Tonight, we're going to explore one of the most fundamental questions humans have ever asked. How many stars exist? It sounds simple enough, but the answer is so staggering that it challenges everything about how we understand numbers, scale, and our place in existence. By the end of this journey, you'll not only know the answer, but you'll understand why it matters and what it reveals about the cosmos we inhabit. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's dive in. Let's begin with something you do every day without thinking about it. Estimating quantities. When you walk into a room, your brain automatically assesses how many people are there. 5 people? 20? Your estimate is probably pretty good, up to about 15 or 20 people. Beyond that, things get fuzzy. Is it 40 people or 60? Most of us genuinely can't tell without counting. This limitation isn't a failure of intelligence. It's how human cognition evolved. Our ancestors needed to assess immediate threats and opportunities. How many predators? How many members of my tribe? How many animals in that herd? These numbers rarely exceeded a few dozen. We never evolved the mental machinery to intuitively grasp thousands, let alone millions or billions. When someone tells you a stadium holds 70,000 people, you accept it intellectually, but you don't feel what 70,000 means. You can't picture it the way you can picture 5 people standing in front of you. And this creates a problem when we start talking about stars, because the numbers involved are so fantastically large that they exist completely outside our intuitive understanding. So before we can discuss how many stars exist, we need to build a framework for understanding large numbers. We need to feel the difference between a million, a billion, and a trillion, because without that foundation, the final answer will just be noise. A million seconds is 11.5 days. You could count to a million in less than 2 weeks if you never stopped to sleep or eat. It's a marathon, certainly, but it's conceivable. You can imagine devoting 11 days to a task. A billion seconds is 32 years. If you started counting the moment you were born and never stopped, you'd reach 1 billion in your early 30s. The entire span from infant to adult would be consumed by this single task. What seemed like a big number with a million has become something that spans a human lifetime. A trillion seconds is 31,700 years. To count that high, you'd need to have started before the invention of agriculture, before writing, before civilization itself. You'd have been counting when humans still lived in small nomadic bands during the last ice age. Every empire that ever rose and fell happened while you counted. Every war, every peace treaty, every technological innovation from the wheel to the smartphone occurred during your count, and you still wouldn't be finished. The difference between a million and a billion is 1,000 times. The difference between a billion and a trillion is another 1,000 times. These aren't just bigger numbers. They're different categories of magnitude entirely. Now here's the difficult part. When we talk about the number of stars in the universe, we're dealing with numbers that make a trillion look quaint. We're talking about hundreds of billions of trillions. Numbers so large that even the trillion comparison fails to convey their scale. But we're getting ahead of ourselves. Let's start with what we can actually see. On a truly dark night, far from city lights, you can see between 2,000 and 5,000 stars with your naked eye. The exact number depends on your location, your eyesight, and how long you let your eyes adjust to the darkness. Let's say 4,000 to be generous. 4,000 stars. That's the extent of what ancient humans could see. That's what philosophers and astronomers worked with for thousands of years. And here's what's remarkable. Every single one of those visible stars is in our galaxy. Not scattered throughout the universe, just in the Milky Way. In fact, they're all relatively nearby in cosmic terms, within a few hundred light years of Earth. You're not seeing the universe when you look up at the night sky with your naked eyes. You're seeing your immediate neighborhood. The Milky Way is a barred spiral galaxy. Picture a disk with a bar-shaped dense region in the middle and spiral arms curving outward. Our Sun sits in one of those spiral arms, about 26,000 light-years from the galactic center. That's roughly 153 quintillion miles, or 246 quintillion kilometers, from the dense core, where stars are packed far more tightly together than in our region. When you see that faint band of light stretching across the sky on a dark night, that milky glow that gives our galaxy its name, you're looking edge-on through the disk. You're seeing the combined light of millions of stars too distant and dim to resolve individually, all blending into a soft, luminous river across the heavens. Everything you can see with your unaided eyes, every constellation, every bright star, all of it exists within a tiny bubble around Earth. The farthest star visible without a telescope is about 16,000 light-years away. The Milky Way is 100,000 light-years across. You're seeing less than 1% of our galaxy's volume. This is where telescopes changed everything. When Galileo first turned a telescope skyward in 1609, he discovered something that shook the astronomical community. That Milky Band wasn't a cloud of glowing gas. It was stars. Countless individual stars, too faint for the naked eye, but perfectly clear through his primitive telescope. Every improvement in optics revealed more. Bigger lenses collected more light, showing fainter objects. Better manufacturing created clearer images, and the count kept climbing. Thousands became tens of thousands. Tens of thousands became millions. So, how many stars are actually in the Milky Way? This is harder to answer than you might think, and the difficulty reveals something important about the challenge of counting cosmic objects. First, we can't see most of our galaxy. Dust clouds block our view in many directions. When you look toward the galactic center, you're peering through thousands of light-years of dust. It's like trying to see through fog. The light from distant stars gets absorbed before reaching us. Second, most stars are dim, really dim. Red dwarf stars, which make up about 70 to 75% of all stars, are so faint that none are visible to the naked eye despite being extremely common. If you could see all the red dwarfs in our local region of the galaxy, the night sky would be packed with stars, thousands of them where you currently see dozens. Third, we're inside the thing we're trying to measure. Imagine being in the middle of a dense forest and trying to count all the trees. You can count nearby trees fairly easily, but distant ones are hidden behind the ones closer to you. And the forest extends in all directions beyond what you can see. Astronomers use several methods to work around these problems. They count stars in small regions where they have good visibility and multiply by the total area. They measure the total mass of the galaxy using gravitational effects and estimate what fraction of that mass is stars versus gas, dust, and dark matter. They study other spiral galaxies similar to ours and use those as templates. All methods have uncertainties, but they converge on a consistent range. The Milky Way contains between 150 billion and 250 billion stars. Most estimates cluster around 200 billion. 200 billion stars in our galaxy alone. If you counted them at 1 per second, it would take over 6,000 years. You'd need to have started counting before the pyramids were built. Think about what this means. You can see maybe 4,000 stars on the darkest night, but they're swimming in a sea of 200 billion stars you cannot see. For every star visible to your naked eyes, there are 50 million invisible ones. The galaxy is incomprehensibly more populated than the night sky suggests. Now, here's where things get truly mind-bending. For most of human history, people didn't know other galaxies existed. When astronomers in the 1700s and 1800s looked at fuzzy patches in the sky, they called them nebulae and assumed they were gas clouds within the Milky Way. Some were indeed gas clouds, but others were something far more extraordinary. The Andromeda Galaxy is visible as a faint smudge to the naked eye on dark nights. For centuries, it was just another nebula. Then in 1923, Edwin Hubble made a discovery that revolutionized our understanding of the universe. Using the 100-inch Hooker telescope at Mount Wilson Observatory, Hubble found a Cepheid variable star in Andromeda. Cepheid variables are pulsating stars with a special property. The time it takes them to brighten and dim is directly related to their actual luminosity. Measure the pulsation period and you know how bright the star really is. Compare that to how bright it appears from Earth, and you can calculate its distance. When Hubble did this calculation, he got a shocking result. Andromeda was roughly 900,000 light-years away in his initial estimate. We now know it's actually 2.5 million light-years distant, or about 14.7 quintillion miles, roughly 23.7 quintillion kilometers. His measurement was off because he didn't know the exact relationship between period and luminosity. But the key point was established beyond doubt. Andromeda couldn't possibly be inside the Milky Way. It was an entirely separate galaxy, a whole other collection of hundreds of billions of stars, existing far beyond our own. The universe, in that moment, became incomparably larger than anyone had imagined. The Milky Way wasn't the universe. It was just one galaxy among many. Once astronomers knew what to look for, they found galaxies everywhere. Point a telescope at any patch of seemingly empty sky, and you'd find dozens, hundreds, sometimes thousands of galaxies. The universe was filled with them, but how many? And more importantly, how many stars did all those galaxies contain? In the 1990s, astronomers conducted an audacious experiment. They pointed the Hubble Space Telescope at a tiny patch of sky in the constellation Ursa Major. This patch appeared completely empty to the naked eye and even to most telescopes. It was so small it could be covered by a grain of sand held at arm's length. Hubble stared at this empty patch for 10 days straight, collecting every photon of light that reached it. The resulting image was called the Hubble Deep Field, and it was revolutionary. In that tiny empty patch, Hubble found about 3,000 galaxies. 3,000 whole galaxies in a region of sky you could cover with a pinhead held at arm's length. Most were incredibly distant, billions of light-years away. Their light had been traveling for most of the age of the universe to reach us. Do the math. If there are 3,000 galaxies in such a tiny region, and you need about 12 million such regions to cover the entire sky, that suggests tens of billions of galaxies in the observable universe. Later observations went deeper. The Hubble Ultra Deep Field found about 10,000 galaxies in an even smaller patch. The Hubble Extreme Deep Field pushed deeper still. And in 2016, a team analyzed all available data and arrived at a new estimate: about 2 trillion galaxies in the observable universe. This number comes primarily from data collected between 2010 and 2020. The James Webb Space Telescope, which began operations in 2022, is still refining these estimates. Early results suggest the count is in the right ballpark, though some very distant, faint galaxy populations may have been missed in earlier surveys. Think of this as our best current estimate, accurate to within perhaps a factor of 2 or 3. 2 trillion galaxies, each one containing anywhere from a few billion to over a trillion stars. The diversity is staggering. Dwarf galaxies with only a few billion stars. Spiral galaxies, like the Milky Way with a few hundred billion. Giant elliptical galaxies with several trillion stars each. What's the average? If you weight by stellar mass and account for the many small galaxies we know exist but are hard to detect, the typical galaxy probably contains around 70 to 100 billion stars. Let's use 100 billion as a round number, acknowledging that this is approximate. 2 trillion galaxies times 100 billion stars per galaxy equals 200 billion trillion stars. Written out, that's 200,000 million stars. In scientific notation, it's 2 times 10 to the 23rd power. Let me try to give you some perspective on this number, but I'll warn you up front. It won't really work. The number is too large to grasp intuitively, but we can at least try to gesture toward its magnitude. There are approximately 7.5 quintillion grains of sand on all of Earth's beaches. That's 7.5 billion trillion grains. For every grain of sand on every beach, there are about 27 stars in the observable universe. Some popularizations say 30 stars per grain. Others say closer to 10. The exact ratio depends on which sand estimate you use, but the order of magnitude is correct. Roughly 10 to 100 stars for each grain of beach sand on Earth. Pick up a handful of sand next time you're at the beach. You're holding perhaps a few thousand grains. For each one of those tiny specks, there are dozens of stars scattered across the cosmos. Each star, a massive ball of nuclear fire, most likely surrounded by planets, existing in a galaxy somewhere in the observable universe. If every person currently alive started counting stars right now, and each person counted 1 star per second without stopping, it would take humanity nearly 800 years to count them all. Generations would be born and die during the count. Entire civilizations could rise and fall, and we'd still be counting. But here's what makes this even more extraordinary. That number, 200 billion trillion stars in the observable universe, might be a dramatic undercount of the total number of stars that exist. The observable universe is the region of space from which light has had time to reach us since the Big Bang. The universe is about 13.8 billion years old. Light travels at 186,000 miles per second, or 300,000 kilometers per second. In 13.8 billion years, you might think light could travel 13.8 billion light years. But the universe has been expanding while that light was traveling. Space itself has been stretching, carrying galaxies with it. By the time light from very distant objects reaches us, those objects have moved much farther away than they were when the light was emitted. The edge of the observable universe is therefore not 13.8 billion light-years away. It's about 46.5 billion light-years in every direction. The observable universe has a diameter of about 93 billion light-years, or roughly 546 sextillion miles, approximately 879 sextillion kilometers. This is our horizon. Beyond this distance, light hasn't had time to reach us yet. Not because those regions don't exist, but because the light is still in transit or, in some cases, will never reach us because space is expanding faster than light can traverse it. Here's the critical question. Does the universe end at the edge of the observable universe, or does it continue beyond that horizon? Most evidence suggests it continues, possibly much farther, perhaps infinitely far. If the universe is infinite, then the number of stars is also infinite, literally infinite. Not just a very large number, but an endless quantity. There would be infinitely many galaxies, each containing billions or trillions of stars, stretching on forever in all directions. In an infinite universe, every possible configuration of matter would occur somewhere, and it would occur infinitely many times. There would be infinitely many galaxies, identical to the Milky Way. Infinitely many planets identical to Earth. Infinitely many versions of you reading these exact words right now. This sounds like science fiction, but it's a serious implication of an infinite universe with roughly uniform matter distribution. If space goes on forever and matter is spread out evenly on average, every possible arrangement must eventually repeat. We don't know if the universe is actually infinite. We can't see beyond the observable universe, so we can't measure whether space continues indefinitely. Current cosmological models are consistent with either a finite but extremely large universe or an infinite one. The data doesn't yet distinguish between these possibilities. What we can say with confidence is that the observable universe contains approximately 200 billion trillion stars. Everything beyond that is speculation, though educated speculation based on our best understanding of cosmology. Let's shift perspective and think about what these stars actually are, because understanding their nature makes their number even more impressive. A star is a sphere of plasma, a state of matter so hot that electrons are stripped from atoms, creating an ionized gas. This plasma is held together by the star's own gravity. And at the core, if the star is massive enough and hot enough, nuclear fusion occurs. Our Sun fuses hydrogen into helium in its core. Every second, about 600 million metric tons of hydrogen are converted to helium. In the process, about 4 million metric tons of mass are converted directly into energy following Einstein's equation E equals mc squared. That energy works its way from the core to the surface over thousands of years, bouncing between particles in the dense interior before finally radiating into space as light and heat. The photon that hits your face on a sunny day was created in the Sun's core tens of thousands of years ago. The Sun has been doing this for 4.5 billion years and will continue for another 5 billion before exhausting its core hydrogen. At that point, it will swell into a red giant, probably engulfing Mercury and Venus and possibly Earth, before shedding its outer layers and leaving behind a white dwarf that will cool over trillions of years. This is just one star, one ball of plasma converting mass to energy through nuclear fusion. And there are 200 billion trillion of them. The total power output is almost incomprehensible. The Sun produces about 380 trillion watts. If every star produced similar power, which is roughly correct on average, the total output would be about 7.6 times 10 to the 49th watts. That's 76,000 billion trillion watts, flooding through space constantly. Not all stars are like the Sun. They come in a spectacular range of sizes, temperatures, colors, and lifetimes. Red dwarf stars are the most common, making up 70 to 75% of all stars. They're small, with masses between 8% and 50% of the Sun's mass, and they burn their fuel incredibly slowly. A red dwarf can shine for trillions of years. None that have ever formed have died yet because the universe isn't old enough. Every red dwarf ever born is still alive today. If 3/4 of 200 billion trillion stars are red dwarfs, that's about 150 billion trillion red dwarfs scattered across the cosmos. None visible to the naked eye from Earth, despite being the most numerous stellar type in existence. Yellow dwarf stars like our Sun make up about 7 to 8% of all stars. They live for roughly 10 billion years before dying. That's still about 14 billion trillion sun-like stars in the observable universe. Then you have the massive stars. Blue and white giants and supergiants, some over 100 times the Sun's mass. These are rare, perhaps 1% of all stars, but spectacularly bright. A single massive blue star can outshine 100,000 suns. These stars live fast and die young, exploding as supernovae after only a few million years. The most massive stars live for only a few million years. They're so rare and short-lived that at any given moment, there might be only a few billion of them in the entire observable universe. That sounds like a lot until you remember it's a tiny fraction of the total. Then you have stellar corpses, white dwarfs, the cooling remnants of stars like the Sun, neutron stars, the crushed cores left by supernova explosions, black holes, collapsed stars where gravity has become so strong that not even light can escape. These aren't actively fusing elements anymore, but they're still there, still part of the census. When we count stars, we're counting all of these. Newborn stars just forming from gas clouds, middle-aged stars steadily fusing hydrogen, dying giants, stellar remnants. The number includes the full diversity of stellar evolution, from birth to death. Now let's talk about planets, because stars rarely exist in isolation. Most have planetary systems. Until 1995, we knew of only one planetary system, ours. We suspected other stars had planets, but couldn't detect them. Then in that year, astronomers found the first confirmed planet orbiting a sun-like star. It was a gas giant, about half Jupiter's mass, orbiting very close to its parent star. Since then, discoveries have exploded. The Kepler Space Telescope, operating from 2009 to 2018, found thousands of exoplanets by watching stars dim slightly when planets passed in front of them. As of 2025, we've confirmed over 6,000 exoplanets with thousands more candidates awaiting verification. The data reveals something remarkable. Planets are common, very common. Most stars have at least one planet. Many have multiple planets. Planetary systems appear to be the default outcome of star formation, not a rare exception. If most of 200 billion trillion stars have planets, the number of planets likely exceeds the number of stars. There might be 300 billion trillion planets, maybe more. The universe is not just filled with stars, it's filled with worlds. We're particularly interested in rocky planets in habitable zones, the regions around stars where temperatures allow liquid water to exist on a planet's surface. Water is essential for life as we know it. Based on Kepler data, roughly 20 to 50% of Sun-like stars have at least one rocky planet in the habitable zone. Let's be conservative and say 20%. 20% of 14 billion trillion Sun-like stars is about 3 billion trillion potentially habitable planets. 3 million billion worlds where conditions might be right for life. That doesn't mean all these planets have life. Habitability requires more than just the right temperature. You need the right atmosphere, protection from radiation, geological activity to recycle nutrients, probably a magnetic field, and likely many other factors we don't fully understand. But even if only a tiny fraction develop life, the absolute numbers could be staggering. If 1 in a million habitable planets has life, that's still 3 quadrillion living worlds. If 1 in a billion develops intelligent life capable of building civilizations, that's still 3 trillion technological societies. These are wild speculations. Our sample size for life is 1, Earth. We have no idea how common or rare the origin of life actually is. We don't know the odds of evolution producing intelligence. We don't know how long civilizations typically last before destroying themselves or dying out. But the sheer number of opportunities is what matters. With planets numbering in the hundreds of billions of trillions, even extremely low probabilities could produce vast amounts of life simply through the law of large numbers. And yet, we found no evidence of other life. No radio signals, no megastructures, no obvious signs of industrial civilizations. The universe appears silent. This is the Fermi Paradox, named after physicist Enrico Fermi's famous question, where is everybody? If there are billions or trillions of potential habitats for life, and the universe has had 13.8 billion years for life to arise and evolve, we should see evidence of other civilizations. The fact that we don't is puzzling. Maybe life is extraordinarily rare, and we're alone or nearly alone. Maybe intelligence is the rare step. Maybe civilizations inevitably destroy themselves. Maybe they're hiding. Maybe the distances between stars are simply too vast for contact to be practical. We don't know. What we do know is that the number of stars and planets provides ample opportunity for life to exist elsewhere, even if we haven't found it yet. Let's talk about how stars create the elements that make planets and life possible, because this connects us directly to those 200 billion trillion stars in a profound way. In the first few minutes after the Big Bang, the universe was hot enough for nuclear fusion to occur throughout space, not just in stars. This created hydrogen, helium, and tiny amounts of lithium. That's it. 3 elements total. Everything else, every other element on the periodic table, was created later inside stars. Carbon, nitrogen, oxygen, the elements essential for life, were forged in stellar cores through nuclear fusion. Iron and nickel were created in the final stages of massive stars' lives. The heaviest elements, gold, platinum, uranium, were synthesized in supernova explosions and neutron star collisions. Stars are element factories. They take simple hydrogen and helium and fuse them into progressively heavier elements. When massive stars explode, they scatter these elements into space. That enriched material mixes with existing gas clouds and eventually forms new stars and planets. This cycle has been operating for over 13 billion years. Each generation of stars enriches the cosmos slightly more. The first stars contained almost pure hydrogen and helium. The Sun, formed about 4.5 billion years ago, contains about 2% heavy elements by mass. That small percentage made Earth possible. Rocky planets require heavy elements. Life requires carbon, oxygen, nitrogen, phosphorus, and many others. Every atom in your body except hydrogen was created inside a star. The oxygen you breathe was forged in stellar cores billions of years ago. The calcium in your bones came from dying stars. The iron in your blood was synthesized in supernova explosions. You are, quite literally, made of processed stardust. This isn't poetic language. It's chemical fact. The atoms that compose you were created through nuclear fusion in stellar interiors, scattered into space when those stars died, incorporated into a gas cloud that eventually collapsed to form the sun and planets, accreted onto Earth, and ultimately became part of living organisms. With 200 billion trillion stars operating as element factories over billions of years, the universe has produced staggering quantities of heavy elements. There's enough carbon for countless rocky worlds, enough oxygen for atmospheres and oceans on billions of planets, enough silicon and iron for planetary crusts and cores across the cosmos. The number of stars directly translates to the total chemical enrichment of the universe. More stars means more fusion, more element production, more raw material for complex chemistry, and potentially for life. Let's zoom out and look at how these stars are distributed across space, because they're not scattered randomly. They're organized into structures at multiple scales. Stars cluster into galaxies. Galaxies cluster into groups and clusters. Clusters organize into superclusters. And superclusters arrange themselves along filaments separated by vast voids. Our Milky Way belongs to the local group, containing about 54 galaxies. Besides the Milky Way and Andromeda, the rest are mostly dwarf galaxies with a few billion stars each. The local group is part of the Laniakea supercluster, which contains about 100,000 galaxies spread across 520 million light-years, or about 3 quadrillion miles, roughly 4.9 quadrillion kilometers. Laniakea isn't bound by gravity. It's defined by galaxies' motions toward a common gravitational center called the Great Attractor. If you could map the entire observable universe, it would look like a cosmic web. Filaments of galaxies forming interconnected strands with enormous voids between them. The structure resembles soap foam. Galaxies concentrate in thin sheets and filaments like soap film, while the voids are like air inside bubbles, mostly empty. This structure arose from tiny density fluctuations in the very early universe. Slightly denser regions attracted more matter through gravity, becoming denser still, while less dense regions lost matter to their denser neighbors. Over billions of years, this created the web of filaments and voids we see today. The largest known structure is the Hercules Corona Borealis Great Wall, a filament of galaxies about 10 billion light-years long, or roughly 59 octillion miles, approximately 95 octillion kilometers. It's so large that it challenges our understanding of cosmic structure formation. When you think about 200 billion trillion stars, remember they're not evenly distributed. Most exist along these filaments and in clusters at the filaments' intersections. The voids contain relatively few galaxies. If you picked a random point in space, you'd probably land in a void, far from any galaxy. The universe is mostly empty. Stars, for all their vast numbers, occupy only a tiny fraction of the total volume of space. Let's think about the future, because the number of stars won't stay constant. Stars are born and die constantly, and the balance between birth and death is shifting. Star formation peaked about 10 to 11 billion years ago when the universe was roughly 3 billion years old. Galaxies were smaller, denser, and gas-rich. Stars formed at a furious pace. Since then, the rate has declined. Much available gas has been consumed or dispersed. What remains is less efficient at forming stars. Currently, the Milky Way forms about 3 to 5 new stars per year. That might seem small, but multiply across 2 trillion galaxies and you get trillions of new stars being born annually across the observable universe. Eventually, star formation will slow further and then cease. Galaxies will exhaust their gas reserves. The last stars will form perhaps 1 trillion years from now, give or take. After that, no new stars will be born. Existing stars will continue shining for a while. Red dwarfs will last for trillions of years, but eventually they too will die. In about 100 trillion years, star formation will have ended, and most stars will have burned out. The universe will be much darker, populated mainly by white dwarfs, brown dwarfs, neutron stars, and black holes. In the far future, measured in timescales that make the current age of the universe look like an eye blink, the last stars will fade. The universe will go dark. But that's so distant it's almost meaningless to contemplate. For now, and for billions of years to come, stars will continue lighting up the cosmos. The number we count today will remain roughly stable, shifting slightly as stars are born and die, but maintaining the same order of magnitude. Let's return to Earth and think about what all this means for us personally. You're standing on a planet orbiting one star among 200 billion trillion. Your sun is utterly typical, a yellow dwarf of average size and brightness. Your location is unremarkable, in the suburbs of a standard spiral galaxy in an ordinary part of the universe. From a cosmic perspective, you're insignificant. Your entire civilization has existed for perhaps 10,000 years, if we're generous. Modern industrial society is only about 250 years old. We've known about other galaxies for barely 100 years. In cosmic terms, we just got here. And yet, we've measured the universe. We've counted the stars. We've calculated distances to galaxies billions of light years away. We've understood our place in the cosmic structure. We're tiny and brief, but we're also capable of comprehending the immensity that contains us. That capability is extraordinary. We're matter that has become conscious of itself, atoms arranged in such a way that they can ponder the nature of atoms, products of the universe that can understand the universe that created them. When you look up at the night sky, you're seeing photons that traveled for years from distant stars. Light that left Sirius 8.6 years ago when you were younger. Light from Betelgeuse that departed 550 years ago during the Renaissance. Ancient photons completing journeys measured in centuries, just to enter your eye and be absorbed by your retina, creating the sensation of seeing a star. You're connected across space and time to those distant suns. The atoms in your body were forged in stars that died before the sun existed. You're made of materials created inside some of those 200 billion trillion stars, recycled through multiple generations, eventually ending up on Earth and incorporated into living tissue. This perspective can be humbling. Your problems, whatever they are, occur on one small world among countless worlds. Your concerns are temporary and local. The universe doesn't notice your struggles. But this perspective can also be freeing. You don't carry cosmic significance on your shoulders. You're allowed to be small. You're allowed to have small joys and small sorrows. You don't need universal importance to matter. You matter to yourself and to those around you, and that's enough. Understanding the number of stars gives context. You're part of something vast and ancient, but you're also here, now, experiencing this moment. That experience has value regardless of cosmic scale. Let's bring this to a close by reflecting on the journey we've taken. We started with a simple question: how many stars exist? The answer, refined through decades of observations with ever more powerful telescopes and updated with the latest data from missions like the James Webb Space Telescope, is approximately 200 billion trillion stars in the observable universe. That number comes from roughly 2 trillion galaxies, each containing on average around 70 to 100 billion stars, though with enormous variation. This is our best estimate as of 2025. It may change as JWST and future telescopes probe deeper, finding faint galaxy populations we've missed. But the order of magnitude is solid. We're talking about something in the range of 1 to a few hundred billion trillion stars. That number is larger than grains of sand on all Earth's beaches by a factor of roughly 20 to 100. It's larger than the number of humans who have ever lived by a factor of about 2 million. It's so large that counting them at 1 per second would take far longer than the current age of the universe. Each of those stars is a massive fusion reactor, converting hydrogen to helium and heavier elements, pumping energy into space, possibly hosting planets, potentially fostering life. Each has its own story, from formation in a collapsing gas cloud to eventual death as a white dwarf, neutron star, or black hole. And all of this, all 200 billion trillion stars, exists within the observable universe, the region from which light has had time to reach us. Beyond that horizon, there may be vastly more. The universe might be infinite, containing infinite stars. Or it might be finite, but much larger than what we can see. We don't know yet. But before we conclude, let's explore several crucial aspects of stars and galaxies that will deepen your appreciation for this cosmic census. Understanding how stars form, live, and die, how we actually measure distances to galaxies, and what different types of galaxies exist will transform that abstract number into something more concrete. Let's start with star formation, because every one of those 200 billion trillion stars was born from a cloud of gas and dust. The process is both elegant and violent. Stars form in molecular clouds, vast regions of space filled with hydrogen gas and dust particles. These clouds are cold, typically around -430 degrees Fahrenheit or -257 degrees Celsius, just a few degrees above absolute zero. They're dark because dust blocks visible light, though infrared telescopes can peer through. Some molecular clouds are enormous. The Orion Molecular Cloud Complex spans hundreds of light years and contains enough material to make over 100,000 sun-like stars. You can see part of it with the naked eye. The middle star in Orion's sword isn't a star at all. It's the Orion Nebula, a stellar nursery where new stars are actively forming right now. Here's how it happens. Something disturbs the cloud. Maybe a nearby supernova explosion sends a shockwave through space. Maybe two clouds collide. Maybe the cloud just gets dense enough that gravity takes over. Whatever the trigger, a region of the cloud starts contracting. As gas falls inward, it heats up. This seems contradictory. How does falling make something hotter? Think of it this way. Gravity converts potential energy into kinetic energy. The gas particles move faster as they fall, and temperature is just a measure of how fast particles are moving. Faster motion equals higher temperature. The contracting region fragments into multiple smaller clumps, each destined to become a star. The center of each clump gets hotter and denser as more material falls in. Eventually, the temperature and pressure at the core become extreme enough for nuclear fusion to begin. Hydrogen nuclei overcome their electrical repulsion and fuse together, forming helium and releasing tremendous energy. When fusion starts, a star is born. The energy from fusion creates an outward pressure that balances the inward pull of gravity. The star reaches equilibrium and can shine steadily for millions or billions of years, depending on its mass. The process leaves behind a rotating disk of leftover material around the new star. This disk is where planets form. Dust particles collide and stick together, growing from sand grains to pebbles, to boulders, to mountains, to moon-sized objects, to planets. The whole process takes maybe 10 million years for rocky planets, possibly longer for gas giants. This is happening across the universe constantly. Right now, in molecular clouds throughout the cosmos, gravity is pulling gas together. Protostars are forming. Disks are coalescing into planets. In the Milky Way alone, several new stars are born each year. Multiply by 2 trillion galaxies, and you get trillions of stars being born annually. But stellar birth rates have varied dramatically over cosmic history. In the early universe, the first stars formed from pure hydrogen and helium. These population 3 stars, as they're called, were probably massive, perhaps 100 to 1,000 times the Sun's mass. They lived fast, burned bright, and exploded as supernovae after only a few million years. Those explosions scattered the first heavy elements into space. Carbon, oxygen, silicon, iron, created through fusion in stellar cores and in the violence of the supernova itself, mixed with the primordial hydrogen and helium. The next generation of stars formed from slightly enriched material. Over billions of years, through countless generations of stars being born and dying, the universe became progressively enriched with heavy elements. By the time the Sun formed 4.5 billion years ago, the local gas cloud contained about 2% heavy elements by mass. That small percentage made all the difference. Those elements allowed rocky planets to form and provided the materials necessary for complex chemistry and life. Today's star-forming regions produce stars with a wide range of masses following what's called the initial mass function. Most stars are small red dwarfs. Fewer are sun-like yellow dwarfs. Massive stars are rare. This distribution appears to be fairly universal across different galaxies and different epochs of cosmic history. Now let's talk about stellar evolution, because stars don't stay the same throughout their lives. They change dramatically depending on their mass, and understanding these changes helps explain the diversity we see. Consider a star like the Sun. For about 10 billion years, it fuses hydrogen to helium in its core. This is the main sequence phase, the stable period that makes up most of a star's life. During this time, the energy from fusion balances gravity and the star shines steadily. Eventually, the core runs out of hydrogen. Fusion stops at the center, and without that outward pressure, the core contracts. This contraction heats it up. Meanwhile, hydrogen fusion continues in a shell around the inert helium core. The energy from this shell fusion is actually greater than the energy the star was producing before, and this causes the outer layers to expand dramatically. The star becomes a red giant. Its surface cools, which is why it's red, but its size increases enormously. The Sun will swell to about 100 times its current diameter, probably engulfing Mercury and Venus. Earth might survive, though it will be scorched and lifeless. As the core continues contracting and heating, it eventually gets hot enough to fuse helium into carbon and oxygen. This happens in a violent event called the helium flash for stars like the Sun. For more massive stars, helium fusion begins more gently. Either way, the star now has 2 active fusion zones: helium fusing to carbon and oxygen in the core, hydrogen fusing to helium in a surrounding shell. This phase doesn't last long, maybe a few 100 million years. When the helium runs out, the core contracts again. For stars like the Sun, this is the end of fusion. The core isn't hot enough or massive enough to fuse carbon. Instead, it becomes a white dwarf, a dense ball of carbon and oxygen about the size of Earth, but containing about half the Sun's mass. The outer layers drift off into space, creating a beautiful planetary nebula. Despite the name, planetary nebulae have nothing to do with planets. Early astronomers thought they looked like the disks of planets through small telescopes, hence the name. They're actually shells of glowing gas being pushed away by radiation from the dying star's hot core. The white dwarf cools over trillions of years, eventually becoming a black dwarf, a cold, dark cinder. Though the universe isn't old enough yet for any black dwarfs to exist, every white dwarf that's ever formed is still glowing. Now, consider a more massive star, say 10 times the Sun's mass. The early stages are similar. Main sequence fusion of hydrogen to helium. Then red giant phase. But massive stars have enough core mass to go further. After helium burning, the core contracts and heats up enough to fuse carbon. Then oxygen. Then neon, magnesium, silicon, and finally iron. Each fusion stage produces elements with progressively higher atomic numbers, and each stage happens faster than the last. A massive star might spend millions of years fusing hydrogen, 1,000,000 years fusing helium, thousands of years on carbon, hundreds of years on oxygen, a year on silicon, and only days fusing silicon to iron. The final stages happen incredibly rapidly. Iron is where fusion stops. Fusing iron doesn't release energy. It consumes energy. So when the core fills with iron, there's no more fuel. No fusion means no outward pressure. Gravity wins. The core collapses in less than a second. It falls from about the size of Earth to about 12 miles or 20 kilometers across. Electrons and protons are crushed together, forming neutrons. The collapse halts when the core becomes a neutron star, so dense that a teaspoon of neutron star material would weigh about 900 billion kilograms on Earth. The collapse happens so rapidly that the outer layers of the star are still falling inward when the core rebounds. Material slams into the rebounding core and bounces back outward in the most violent explosion in the universe, short of the Big Bang itself, a supernova. For a few weeks, a single supernova can outshine an entire galaxy. It releases more energy in that brief period than the Sun will produce in its entire 10 billion year lifetime. The explosion scatters the star's outer layers into space at speeds of 10,000 miles per second or 16,000 kilometers per second. Those layers contain all the heavy elements created in the star's life and in the explosion itself. If the original star was massive enough, the core collapses beyond a neutron star into a black hole. The core mass required is probably around 3 times the Sun's mass, though the exact threshold is still debated. Above that limit, nothing can stop the collapse. The core shrinks to a point, creating a region of space where gravity is so strong that not even light can escape. This entire cycle, from star formation to supernova or planetary nebula, has played out countless times across cosmic history. With 200 billion trillion stars existing at various stages of evolution, millions are dying every day across the observable universe. Millions more are being born to replace them. Let's discuss how we actually measure distances to galaxies, because this measurement is crucial for counting them and estimating total stars. Without accurate distances, we can't distinguish between a nearby faint galaxy and a distant bright one. We can't calculate the volume of space we're surveying. We can't extrapolate from small regions to the entire universe. Astronomers use what's called the cosmic distance ladder, a series of overlapping measurement techniques that build on each other. The first rung is direct measurement using parallax. As Earth orbits the Sun, nearby stars appear to shift position slightly relative to more distant background stars. The closer the star, the bigger the shift. Measure that shift, and you can calculate distance using simple geometry. This works well for stars up to a few thousand light-years away. The Gaia space mission has measured parallax distances for about 2 billion stars in the Milky Way with extraordinary precision. But beyond a few thousand light-years, the shifts become too small to measure accurately even for Gaia. The second rung uses standard candles, objects whose intrinsic brightness is known. Cepheid variable stars are the most famous example. Henrietta Leavitt discovered in 1912 that there's a direct relationship between a Cepheid's pulsation period and its intrinsic brightness. Measure the period and you know how bright it really is. Compare that to how bright it appears and you can calculate distance. Hubble used Cepheids to measure distance to Andromeda, proving it was a separate galaxy. The Hubble Space Telescope has found Cepheids in galaxies up to about 100 million light-years away. Beyond that, even the brightest Cepheids become too faint to detect individually. The third rung uses type Ia supernovae. These occur when a white dwarf in a binary system accumulates material from its companion star. When the white dwarf's mass reaches a critical threshold, about 1.4 times the Sun's mass, it explodes in a thermonuclear detonation. Because all type Ia supernovae involve white dwarfs reaching essentially the same mass before exploding, they all have similar intrinsic brightness. They're incredibly luminous, briefly outshining entire galaxies, so they can be seen across billions of light-years. By calibrating type Ia supernovae against Cepheid distances in nearby galaxies, astronomers established that type Ia supernovae work as distance indicators. They've been used to measure distances to galaxies billions of light-years away. For the most distant galaxies, approaching the edge of the observable universe, astronomers use the redshift of light. As the universe expands, light from distant objects gets stretched to longer wavelengths, shifted toward the red end of the spectrum. The more distant the galaxy, the faster it's receding due to cosmic expansion, and the greater the redshift. By measuring a galaxy's redshift and using models of cosmic expansion, astronomers can estimate its distance. This works for galaxies so distant that no individual stars or supernovae can be resolved. Each rung of the distance ladder has uncertainties. Parallax measurements have small errors. Cepheid calibrations aren't perfect. Type Ia supernovae shows some variation in brightness that must be accounted for. Redshift distances depend on models of cosmic expansion that have their own assumptions. But by carefully cross-checking each method against the others and quantifying uncertainties, astronomers have built a reliable distance scale. We can measure distances to nearby galaxies with a few % accuracy and to distant galaxies with maybe 10 to 20% accuracy. That's good enough to count galaxies and estimate the total number of stars. Now let's explore the diversity of galaxies. Because not all galaxies are spiral disks like the Milky Way. They come in several distinct types with different structures and stellar populations. Spiral galaxies have a flat rotating disk with spiral arms where active star formation occurs. They also have a central bulge of older stars and often a bar-shaped structure across the center. The Milky Way is a barred spiral. So is Andromeda, though its bar is less prominent. Spiral arms aren't rigid structures. They're density waves, regions where stars and gas bunch up temporarily as they orbit. Think of a traffic jam on a circular highway. Cars enter the jam from behind, slow down, then accelerate out the front. The jam itself doesn't move around the highway, but individual cars do. Similarly, stars enter spiral arms, spend some time there, then leave. The arms persist as patterns, even though the stars flowing through them constantly change. Star formation happens preferentially in spiral arms because that's where gas gets compressed. The compression triggers collapse of molecular clouds, leading to new star formation. This is why spiral arms look bright and blue. They're full of young, hot, massive stars. Elliptical galaxies have a very different structure. They're ellipsoidal or spherical, blobs of stars with little or no disk structure. They range from small dwarf ellipticals with a few billion stars to giant ellipticals with several trillion stars. Giant ellipticals are thought to form from mergers of multiple smaller galaxies. When galaxies collide, their stars rarely hit each other because the distances between stars are vast. But the gas clouds do collide, triggering intense bursts of star formation. Eventually, the galaxies merge into a single, larger elliptical galaxy. Elliptical galaxies contain mostly old stars. They've used up or lost most of their gas, so star formation has largely ceased. They glow with the yellowish light of old sun-like stars rather than the blue light of young, massive stars. Irregular galaxies lack clear structure. They're messy, chaotic collections of stars and gas. The large and small Magellanic Clouds, satellite galaxies orbiting the Milky Way, are irregular galaxies. Many irregulars are small, dwarf galaxies. Some are galaxies disrupted by gravitational interactions with neighbors. Lenticular galaxies are intermediate between spirals and ellipticals. They have a disk like spirals, but little or no spiral structure and little ongoing star formation. They're sometimes called armless spirals or disk ellipticals. The relative abundance of these types has changed over cosmic history. In the early universe, most galaxies were small and irregular. Over time, they merged into larger spirals and ellipticals. Star formation was more vigorous in the past. Today's universe has more large galaxies and less active star formation than the universe a few billion years ago. When we count 2 trillion galaxies, we're counting all types, tiny dwarf galaxies with a few billion stars, magnificent spirals with hundreds of billions, massive ellipticals with trillions. Each contributes to the total star count. The diversity means our average of 100 billion stars per galaxy is just that, an average. Some galaxies have far fewer, some far more. Let's talk about dark matter and dark energy, because when astronomers measure the mass of galaxies, they find something strange. The visible stars and gas don't account for all the mass. When you measure how fast stars orbit in a galaxy, you can calculate how much mass must be present to provide the necessary gravity to keep those stars in orbit. For the Milky Way and other spirals, the orbital speeds stay high even far from the galactic center. This implies there's a lot of mass out there, but we don't see enough stars and gas to account for it. The visible matter makes up only about 15% of the total mass. The rest is dark matter, material that doesn't emit, absorb, or reflect light. We can't see it directly. We only know it's there because of its gravitational effects. No one knows what dark matter is. It's not ordinary matter made of protons, neutrons, and electrons. It's something else, probably some exotic particle that doesn't interact electromagnetically. Several candidates have been proposed. Weakly interacting massive particles, actions, sterile neutrinos. But despite decades of searching, we haven't directly detected dark matter particles yet. Dark matter dramatically affects galaxy formation and structure. Without it, galaxies would fly apart. The visible stars don't have enough gravity to hold galaxies together given their rotation speeds. Dark matter provides the extra gravitational glue. When we count stars, we're counting only the visible matter. The dark matter doesn't form stars. It just provides gravitational scaffolding that allows galaxies to exist and hold together. Dark energy is even more mysterious. Observations of distant Type Ia supernovae in the late 1990s revealed that the expansion of the universe is accelerating. Something is pushing space apart, overcoming gravity on large scales. That something is dark energy. Dark energy makes up about 68% of the total energy content of the universe. Dark matter is about 27%. Ordinary matter, the stuff that makes stars and planets and us, is only about 5% of the total. Dark energy affects the observable universe's size. It causes space to expand faster, which affects how far we can see and how many galaxies we can count. It's part of the reason the observable universe is larger than 13.8 billion light-years in radius, despite being 13.8 billion years old. So when we talk about 200 billion trillion stars, we're talking about only the visible fraction of the universe's content. Most of the universe is dark matter and dark energy, mysterious substances we don't understand. Stars represent just a small fraction of what's out there. Let's discuss globular clusters, because they offer a unique window into stellar populations and give us a way to visualize large numbers of stars concentrated together. Globular clusters are spherical collections of stars, typically containing hundreds of thousands to a few million stars packed into a volume maybe 100 light-years across, or roughly 588 trillion miles, approximately 947 trillion kilometers. The Milky Way has about 150 globular clusters orbiting in a halo around the galaxy. The stars in globular clusters are ancient, typically 10 to 12 billion years old. They formed in the early days of the galaxy from gas that was metal-poor, containing very few heavy elements. This makes them laboratories for studying stellar evolution in low metallicity environments. The most spectacular globular cluster visible from Earth's northern hemisphere is M13 in Hercules, containing about 300,000 stars. From the southern hemisphere, Omega Centauri is even more impressive with about 10 million stars. Imagine living on a planet orbiting a star in a globular cluster's core. Your night sky would contain thousands of stars bright enough to read by. Some would be close enough to show visible disks rather than mere points of light. The sky would never be truly dark. But such planets are unlikely. Globular cluster stars are old and metal-poor. They probably don't have rocky planets. The frequent gravitational interactions between closely packed stars would destabilize planetary orbits. Globular clusters are beautiful, but probably lifeless. When you observe a globular cluster through a telescope, you're seeing what a million stars look like, concentrated together. It's one of the few ways to actually visualize a large stellar population rather than just knowing it abstractly. That dense ball of light contains 1 million individual suns, each one a nuclear furnace like our own sun, each one potentially billions of years older than our solar system. Multiply that by 200 million, and you approach the total number of stars in the observable universe. 200 million globular clusters like Omega Centauri would give you about the right number. Let's talk about what the night sky looks like from other galaxies, because perspective matters when we think about cosmic scale. From Andromeda, looking back at us, the Milky Way would be visible as a bright spiral galaxy spanning maybe 6 times the diameter of the full moon. Individual bright stars would be visible as tiny points scattered around the spiral structure. Astronomers on a planet in Andromeda would study the Milky Way the same way we study Andromeda, measuring its rotation, mapping its spiral arms, searching for individual stars and clusters. From a galaxy a billion light-years away, the Milky Way would be just another faint smudge among millions, requiring a telescope to see at all. Individual stars would be impossible to resolve. The entire galaxy would be condensed to a point or a small, fuzzy blob. From near the edge of the observable universe, galaxies in our local region would be barely visible, even with powerful telescopes. The light would be extraordinarily redshifted and dimmed by cosmic expansion. An observer there would see a different observable universe centered on their location, overlapping with ours, but extending far beyond it in their direction. This highlights an important point. The observable universe isn't the same for all observers. It's defined by how far light can travel in the age of the universe from each observer's location. An alien astronomer in a galaxy at our cosmic horizon has their own observable universe, different from ours, containing different galaxies that we'll never see. The total number of stars in the universe is therefore much larger than the 200 billion trillion we can count. We can only count stars within our observable bubble. Beyond that horizon are more stars in other galaxies that we simply can't see because their light hasn't had time to reach us yet. If the universe is infinite, the total number of stars is infinite. Our 200 billion trillion represents just the finite sample we can observe from our particular location in space and time. Let's consider the rate at which we're discovering new information about stars and galaxies, because the pace of discovery has accelerated dramatically in recent decades. Before 1995, we knew of no planets outside our solar system. Today, we've confirmed over 6,000 and counting. Before Hubble, we had rough estimates of galaxy counts. Now we have detailed surveys covering millions of galaxies. Before Gaia, our stellar distance measurements were limited. Now we have precise positions and distances for over 1 billion stars. The James Webb Space Telescope, operational since 2022, is pushing boundaries further. It's finding galaxies at extreme distances, seeing further back in cosmic time than Hubble could. Early results have revealed surprisingly massive, well-formed galaxies existing earlier than models predicted. This is causing astronomers to revise theories of galaxy formation. Future telescopes will continue this trend. The upcoming extremely large telescope will have a 39-meter or 128-foot mirror, collecting more light than any current optical telescope. The Nancy Grace Roman Space Telescope will survey huge areas of sky, finding millions more galaxies. Each new instrument refines our census of stars. Each discovery adjusts our estimates slightly. The number 200 billion trillion will be updated as better data comes in, but the order of magnitude is unlikely to change drastically. We're counting stars in the right ballpark, even if the exact number shifts as measurements improve. This progressive refinement is how science works. We make the best estimates we can with available data, then improve those estimates as better data arrives. The number of stars isn't speculation. It's a measurement-based estimate with quantified uncertainties that will continue to improve. What we do know is that the universe is filled with stars in quantities that boggle the mind. More stars than grains of sand on Earth's beaches. More stars than humans have ever looked at the sky since our species began. More stars than we could visit even if we had billions of years and could travel at light speed. And most remarkably, we figured this out. We built telescopes and satellites and detectors sophisticated enough to count galaxies billions of light years away. We developed the mathematics to calculate distances across cosmic scales. We created theories that explain what we see and make testable predictions. That intellectual achievement, measuring the contents of the observable universe from one small planet orbiting one ordinary star, represents one of humanity's greatest accomplishments. We're tiny and brief in cosmic terms, but we're also capable of understanding the vastness that contains us. That capacity for understanding is extraordinary. So when you look up at the stars tonight, remember you're seeing just the nearest neighbors in a cosmos containing 200 billion trillion stars, each one a sun, each one a nuclear furnace converting hydrogen to helium, each one potentially hosting planets, maybe some with life, each one part of the grand cosmic web of galaxies and structures stretching across billions of light years. We've measured this, we've counted them, we've grasped our place among this multitude. That's remarkable. That's extraordinary. That's what makes us human. But let's go deeper into several phenomena that reveal how dynamic and interconnected this stellar population truly is. Understanding binary stars, stellar nurseries in action, the most extreme objects in the cosmos, and how galaxies interact will transform your appreciation for what those 200 billion trillion stars actually do and how they evolve. Most stars don't exist in isolation like our Sun. The majority live in binary or multiple star systems where two or more stars orbit each other, gravitationally bound for billions of years. In a binary system, two stars orbit their common center of mass, performing a gravitational dance that can last for the entire lifetime of both stars. These systems are incredibly common. Roughly half of all Sun-like stars exist in binary or multiple star systems. For more massive stars, the fraction is even higher, perhaps 70 to 80%. Some binaries are wide, with the two stars separated by hundreds of astronomical units, about 100 to 200 times Earth's distance from the Sun, or roughly 9,300,000,000 miles to 18,600,000,000 miles, approximately 15 billion to 30 billion kilometers. These stars orbit each other over thousands of years and barely influence each other's evolution. Other binaries are close, with stars separated by only a few times their own diameters. These systems are fascinating because the stars can exchange material. If one star swells into a red giant, its outer atmosphere might spill over onto its companion. This mass transfer can dramatically affect both stars' evolution. Some close binaries are so tight that the stars actually touch, sharing a common envelope of gas. These contact binaries look like peanuts, two stars merged together, but each maintaining its own core. Binary star systems produce some of the most spectacular events in astronomy. Type Ia supernovae, which we use as distance indicators, occur in binary systems where a white dwarf accumulates material from its companion until reaching critical mass and exploding. Nova outbursts happen when a white dwarf in a binary system accretes hydrogen from its companion. The hydrogen builds up on the white dwarf's surface until conditions are right for explosive fusion. The white dwarf briefly brightens by thousands of times, appearing as a new star in the sky, hence nova meaning new. Then it fades back to normal, only to repeat the cycle years or decades later. Some of the most massive stars exist in binary systems where both stars are giants. When one explodes as a supernova, the explosion can be asymmetric, giving the remnant neutron star or black hole a kick that sends it flying through space at hundreds of miles per second. The remaining companion star might be disrupted or might continue orbiting the compact remnant. Binary systems remind us that stellar populations are interactive. Stars don't just shine in isolation. They interact gravitationally and sometimes physically, exchanging material, influencing each other's evolution, creating phenomena we wouldn't see in single star systems. With 200 billion trillion stars, and roughly half in binary or multiple systems, we're talking about 100 billion trillion binary systems. Each one is unique. Different mass ratios, different orbital periods, different ages, different stages of evolution. The diversity is staggering. Now let's visit stellar nurseries in detail, because these are the factories where those 200 billion trillion stars were born, and where new stars are being created constantly. The Eagle Nebula, made famous by Hubble's Pillars of Creation image, is an active star-forming region about 7,000 light-years from Earth, or roughly 41 quadrillion miles, approximately 66 quadrillion kilometers. Those towering pillars of gas and dust are several light-years tall, or roughly 18 trillion miles, approximately 29 trillion kilometers. They're being eroded by intense ultraviolet radiation from nearby massive young stars, while simultaneously serving as birthplaces for new stars. Inside those pillars, dense clumps of gas are collapsing under their own gravity. Some have already formed protostars, infant stars, not yet hot enough for nuclear fusion. These protostars are surrounded by swirling disks of gas and dust where planets will eventually form. The process is violent. Powerful jets of material shoot out from the protostar's poles, plowing into surrounding gas and creating glowing shockwaves. These jets are driven by magnetic fields threading through the accretion disk. Material spiraling onto the protostar generates intense magnetic fields that channel some of the infalling gas back outward along the rotational axis at speeds of hundreds of miles per second. The Carina Nebula is another spectacular star factory containing some of the most massive stars known. Eta Carinae, possibly the most massive binary star system in our region of the galaxy, contains a star over 100 times the Sun's mass. It's so massive and luminous that it's unstable. In the 1840s, it underwent a massive outburst, ejecting several sun masses of material and briefly becoming one of the brightest stars in the sky, despite being 7,500 light-years away, or roughly 44 quadrillion miles, approximately 71 quadrillion kilometers. Eta Carinae will explode as a supernova sometime in the astronomically near future, perhaps within the next 100,000 years. When it does, it will briefly outshine the full moon despite its vast distance. The explosion will be visible during the day. The Orion Nebula, visible to the naked eye as a fuzzy patch in Orion's sword, is the closest major star-forming region at about 1,300 light-years distant, or roughly 7.6 quadrillion miles, approximately 12.3 quadrillion kilometers. It contains about 700 stars in various stages of formation, from protostars still embedded in their natal gas clouds to young stars less than 1 million years old. The trapezium cluster at the nebula's heart contains 4 bright, massive stars, easily visible through small telescopes. These stars are only about 1 million years old, but already shine with the light of hundreds of thousands of suns. Their intense ultraviolet radiation is ionizing the surrounding gas, making it glow, creating the beautiful nebula we see. In a few million years, the gas will be completely dispersed by stellar winds and radiation, leaving an open cluster of stars like the Pleiades. Eventually, over tens or hundreds of millions of years, gravitational interactions will cause the cluster to dissolve, scattering its stars throughout the galaxy. This cycle plays out across the universe. Molecular clouds collapse, stars form. The most massive stars quickly ionize and disperse the remaining gas. A stellar cluster emerges. Over time, the cluster dissolves. The stars spread out. Eventually, some of those stars die, returning material to space, enriching future generations of clouds that will collapse to form new stars. Star formation rates have varied dramatically over cosmic time. The peak occurred about 10 to 11 billion years ago, when galaxies were smaller, denser, and gas-rich. Back then, the universe was forming stars at perhaps 10 times the current rate. Since that peak, star formation has declined. Much of the available gas has been consumed or dispersed. What remains is in more diffuse reservoirs that form stars less efficiently. The universe today produces perhaps 1/3 as many new stars per year as it did at the peak. This decline will continue. In 1 trillion years, most galaxies will have exhausted their gas reserves. Star formation will sputter out. The last stars will form, then no more. The stellar population will age and gradually fade as long-lived red dwarfs slowly burn through their fuel over trillions of years. But that's so far in the future, it's almost meaningless. For now and for billions of years to come, stellar nurseries across the cosmos continue producing new stars. The 200 billion trillion count includes stars at all ages, from newborns less than 1 million years old to ancient stars formed when the universe was less than 1 billion years old. Let's discuss quasars and active galactic nuclei, because they represent the most extreme stellar environments in the universe and played a crucial role in shaping galaxy evolution. A quasar is a galaxy with an extremely bright core powered by a supermassive black hole accreting material. The black hole, typically a few million to a few billion times the Sun's mass, sits at the galaxy's center. Gas spiraling into the black hole forms an accretion disk heated to millions of degrees. This disk can outshine the entire galaxy's worth of stars, making the quasar visible across billions of light years. Quasars were common in the early universe, but are rare today. Most formed when galaxies were young and gas-rich, providing ample fuel for the central black hole. As galaxies aged and consumed their gas, quasar activity declined. Today's universe has few active quasars compared to the universe a few billion years ago. The brightest known quasar, J100 plus 2802, contains a black hole about 12 billion times the Sun's mass. This black hole formed when the universe was only 900 million years old. How a black hole got that massive, that quickly, is still a puzzle. It requires extremely efficient accretion over a relatively short cosmic time. Quasars affect their host galaxies profoundly. The energy output from the accretion disk drives powerful winds that blow gas out of the galaxy at thousands of miles per second. This quenches star formation by removing the raw material needed to make new stars. This feedback mechanism is thought to regulate galaxy growth. Without it, galaxies would convert all their gas into stars very quickly. The quasar phase acts as a self-limiting process. The black hole grows by accreting gas, which powers winds that blow away the remaining gas, shutting off both star formation and further black hole growth. Most massive galaxies, including the Milky Way, contain supermassive black holes at their centers. Ours is about 4 million times the Sun's mass. It's currently quiescent, not actively accreting much material. But in the past, it probably went through an active phase when it was feeding vigorously and possibly shining as a quasar. Evidence of past activity appears in the Fermi bubbles. Two enormous lobes of hot gas extending 50,000 light-years, or about 294 quadrillion miles, approximately 473 quadrillion kilometers, above and below the galactic plane. These bubbles were probably inflated by past activity of the central black hole, perhaps a few million years ago. Quasars help us study the early universe. Because they're so bright, they can be seen at extreme distances. The most distant quasars known existed when the universe was less than 1 billion years old. Their light has been traveling for over 13 billion years to reach us. By studying quasar spectra, astronomers learn about conditions in the early universe. Light from distant quasars passes through intervening gas clouds on its way to Earth. Each cloud absorbs light at specific wavelengths depending on its chemical composition. By analyzing these absorption features, astronomers map how gas was distributed billions of years ago and how chemical enrichment progressed over time. With 2 trillion galaxies, and probably most containing supermassive black holes, we're talking about trillions of black holes. Most are dormant now, but when we look back in time by observing distant galaxies, we see more active quasars, revealing an epoch when supermassive black holes were growing rapidly and exerting enormous influence on galaxy evolution. Let's explore galaxy collisions and mergers, because galaxies don't exist in isolation. They interact, collide, and merge, dramatically reshaping stellar populations. When 2 galaxies collide, the stars themselves rarely hit each other. Space is mostly empty. The distances between stars are vast compared to stellar sizes. But the gas clouds do collide, and the collision compresses the gas, triggering intense bursts of star formation. The antennae galaxies, about 70 million light-years away, or roughly 412 quadrillion miles, approximately 663 quadrillion kilometers, are a spectacular example. 2 spiral galaxies are in the process of merging. Long tidal tails of stars and gas stream away from the collision site, created by gravitational interactions. Within the collision zone, thousands of young star clusters are forming, each containing tens of thousands of newly born stars. In about 1 billion years, the 2 galaxies will complete their merger, forming a single large elliptical galaxy. The spiral structure will be destroyed. Most of the gas will be consumed in star formation or blown away by supernova winds. The resulting elliptical will be a graveyard of old stars with little ongoing star formation. This process is common. Most large elliptical galaxies probably formed from mergers of smaller spirals. The Milky Way itself has absorbed several small dwarf galaxies over its lifetime. Evidence appears in stellar streams, rivers of stars from destroyed dwarf galaxies now orbiting through the Milky Way's halo. Andromeda and the Milky Way are approaching each other at about 70 miles per second, or 110 kilometers per second. In about 4 billion years, they'll collide. The merger will trigger massive star formation as gas clouds collide. Eventually, after several close passes and perhaps 1 billion years of interaction, they'll merge into a single large elliptical galaxy. Astronomers have already named it Milky. Our sun will likely survive the collision. It'll be thrown into a different orbit, possibly ending up farther from the merged galaxy's center. Earth might survive too, though its orbit around the Sun could be perturbed. The solar system as a whole will probably emerge intact, orbiting in the new galaxy. But the night sky will change dramatically. During the approach, Andromeda will grow larger, eventually spanning several degrees across the sky. When the galaxies interpenetrate, new massive stars will light up the sky. The galactic nuclei will pass close to each other or even merge. For observers on Earth, if Earth still exists and has observers, it will be spectacular. Galaxy interactions are fundamental to cosmic evolution. In the early universe, galaxies were smaller and closer together. Collisions and mergers were common. Large galaxies grew by cannibalizing smaller ones. This hierarchical assembly built the diverse galaxy population we see today. Even now, interactions continue. The Milky Way is slowly tearing apart the Sagittarius dwarf elliptical galaxy, one of our satellite galaxies. The large and small Magellanic Clouds are slowly being disrupted by tidal forces from the Milky Way. In several billion years, they'll likely merge with us. With 2 trillion galaxies in the observable universe, interactions and mergers are happening constantly somewhere. Thousands of galaxy collisions are occurring across the observable universe at any given moment, each one reshaping stellar populations, triggering star formation, building larger galaxies through merger, and contributing to the ongoing evolution of cosmic structure. Let's discuss the cosmic microwave background and the earliest stars, because understanding the universe's infancy gives context to today's stellar census. The cosmic microwave background is light from about 380,000 years after the Big Bang, when the universe first became transparent. Before that, the universe was opaque, a hot plasma where photons couldn't travel far without scattering off electrons. When the universe cooled enough for electrons and protons to combine into neutral hydrogen, light could suddenly travel freely. That light has been traveling through space ever since, stretched by cosmic expansion from visible wavelengths into microwaves. We detect it today as a faint glow coming from all directions with a temperature of about -454 degrees Fahrenheit or -270 degrees Celsius, just a few degrees above absolute zero. The microwave background shows tiny temperature fluctuations, variations of about 1 part in 100,000. These fluctuations represent density variations in the early universe. Slightly denser regions became the seeds of future galaxies and clusters. Slightly less dense regions became voids. The first stars formed about 50 to 200 million years after the Big Bang, condensing from the primordial hydrogen and helium gas in those slightly overdense regions. These population 3 stars were probably very massive, hundreds of times the Sun's mass. They lived fast, perhaps only a few million years, and exploded as supernovae, creating and dispersing the first heavy elements. Those explosions seeded the universe with carbon, oxygen, iron, and other elements, allowing the next generation of stars to form from slightly enriched material. We've never directly observed a population 3 star. They're too rare and too distant. But we see their chemical legacy in old population 2 stars, which contain small amounts of heavy elements clearly made in earlier generations. Finding a surviving population 3 star, if any still exist, is a major goal of modern astronomy. Such a star would tell us about the very first stellar generation and test our theories of star formation in the pristine early universe. The James Webb Space Telescope is searching for the earliest galaxies, hoping to see the epoch when the first stars were lighting up the cosmos. Early results have found galaxies existing just a few 100 million years after the Big Bang, earlier than many models predicted. This is forcing revisions to our understanding of how quickly structure formed in the early universe. Those early galaxies were small, perhaps only a few billion stars each, far smaller than today's giants. But they were the building blocks. Over billions of years, they merged and grew into the large galaxies we see today. The Milky Way is built from hundreds or thousands of smaller galaxies that merged over cosmic history. This hierarchical assembly means the stars in today's galaxies came from many different places. Some formed in the main galaxy, others formed in smaller galaxies that later merged in. The stellar population of any large galaxy is a mixture, a blended history of multiple mergers and accretion events. When we count 200 billion trillion stars today, we're counting the product of 13.8 billion years of star formation, merger, and evolution. That number represents the accumulated stellar population built up over cosmic time in 2 trillion distinct galaxies. Let's examine variable stars in more detail because they reveal stellar physics and help us understand how stars work beyond their surface appearances. We mentioned Cepheid variables earlier, but there are many other types of variable stars, each varying for different physical reasons. RR Lyrae variables are old, low-mass stars that pulsate with periods of a few hours to a day. They're less luminous than Cepheids, but still useful as distance indicators for nearby galaxies and globular clusters. Mira variables are red giants with periods of months to years, varying by factors of 100 or more in brightness. They pulsate because they're unstable. The star's atmosphere expands and contracts, changing the star's surface area and temperature, which changes its brightness. Eclipsing binaries vary because one star periodically blocks the other from our view. Algol, the demon star in Perseus, is a famous example. Every 2.9 days, a dim star passes in front of a bright star, causing Algol to dim noticeably for several hours. Cataclysmic variables undergo sudden outbursts when material from a companion star falls onto a white dwarf. The accretion is unstable, building up until conditions trigger explosive fusion or a sudden increase in accretion rate, causing the system to brighten dramatically. Flare stars, mostly red dwarfs, undergo sudden brightenings lasting minutes to hours when magnetic reconnection events in their atmospheres release enormous amounts of energy. These flares can briefly increase the star's brightness by several times. When we count 200 billion trillion stars today, we're counting the product of 13.8 billion years of star formation, merger, and evolution. That number represents the accumulated stellar population built up over cosmic time in 2 trillion distinct galaxies. Let's examine variable stars in more detail because they reveal stellar physics and help us understand how stars work beyond their surface appearances. We mentioned Cepheid variables earlier, but there are many other types of variable stars, each varying for different physical reasons. RR Lyrae variables are old, low-mass stars that pulsate with periods of a few hours to a day. They're less luminous than Cepheids, but still useful as distance indicators for nearby galaxies and globular clusters. Mira variables are red giants with periods of months to years, varying by factors of 100 or more in brightness. They pulsate because they're unstable. The star's atmosphere expands and contracts, changing the star's surface area and temperature, which changes its brightness. Eclipsing binaries vary because one star periodically blocks the other from our view. Algol, the demon star in Perseus, is a famous example. Every 2.9 days, a dim star passes in front of a bright star, causing Algol to dim noticeably for several hours. Cataclysmic variables undergo sudden outbursts when material from a companion star falls onto a white dwarf. The accretion is unstable, building up until conditions trigger explosive fusion or a sudden increase in accretion rate, causing the system to brighten dramatically. Flare stars, mostly red dwarfs, undergo sudden brightenings lasting minutes to hours when magnetic reconnection events in their atmospheres release enormous amounts of energy. These flares can briefly increase the star's brightness by several times. Each type of variability reveals something about stellar physics. Pulsating variables tell us about stellar structure and instabilities. Eclipsing binaries reveal stellar sizes and masses. Cataclysmic variables show us accretion physics. Flare stars demonstrate magnetic activity. Among 200 billion trillion stars, billions are variable. Monitoring them helps astronomers understand stellar evolution and physics across a wide range of masses, ages, and chemical compositions. Let's discuss neutron stars and pulsars, because these exotic objects represent one endpoint of stellar evolution and display some of the most extreme physics in the universe. A neutron star forms when a massive star's core collapses during a supernova. The collapse crushes protons and electrons together, forming neutrons. The result is a sphere about 12 to 15 miles or 20 to 25 kilometers across, containing about 1.4 times the Sun's mass. The density is staggering. A teaspoon of neutron star material would weigh about 900 billion kilograms. The surface gravity is about 100 billion times Earth's gravity. If you could somehow stand on a neutron star's surface, you'd weigh the same as a small mountain does on Earth. Many neutron stars are pulsars, spinning rapidly and beaming radiation from their magnetic poles like cosmic lighthouses. As the star rotates, the beam sweeps past Earth and we detect a pulse. Some pulsars spin hundreds of times per second, rotating faster than a kitchen blender. The Crab pulsar spins 30 times per second. It's powered by the rotational energy stored in the neutron star. As the pulsar emits radiation, it gradually slows down, losing rotational energy. Eventually, over millions of years, it will slow enough that the emission mechanism shuts off and the pulsar dies. Each type of variability reveals something about stellar physics. Pulsating variables tell us about stellar structure and instabilities. Eclipsing binaries reveal stellar sizes and masses. Cataclysmic variables show us accretion physics. Flare stars demonstrate magnetic activity. Among 200 billion trillion stars, billions are variable. Monitoring them helps astronomers understand stellar evolution and physics across a wide range of masses, ages, and chemical compositions. Let's discuss neutron stars and pulsars, because these exotic objects represent one endpoint of stellar evolution and display some of the most extreme physics in the universe. A neutron star forms when a massive star's core collapses during a supernova. The collapse crushes protons and electrons together, forming neutrons. The result is a sphere about 12 to 15 miles or 20 to 25 kilometers across, containing about 1.4 times the Sun's mass. The density is staggering. A teaspoon of neutron star material would weigh about 900 billion kilograms. The surface gravity is about 100 billion times Earth's gravity. If you could somehow stand on a neutron star's surface, you'd weigh the same as a small mountain does on Earth. Many neutron stars are pulsars, spinning rapidly and beaming radiation from their magnetic poles like cosmic lighthouses. As the star rotates, the beam sweeps past Earth and we detect a pulse. Some pulsars spin hundreds of times per second, rotating faster than a kitchen blender. The Crab pulsar spins 30 times per second. It's powered by the rotational energy stored in the neutron star. As the pulsar emits radiation, it gradually slows down, losing rotational energy. Eventually, over millions of years, it will slow enough that the emission mechanism shuts off and the pulsar dies. The fastest known pulsar spins over 700 times per second. It's in a binary system, where accretion from the companion star has spun it up to extreme speeds. These millisecond pulsars are the most precise clocks in nature. Their rotation is so stable that astronomers use them to detect gravitational waves and test theories of gravity. Magnetars are neutron stars with ultra-strong magnetic fields, 1,000 trillion times Earth's magnetic field. These fields can cause violent outbursts, suddenly releasing enormous amounts of energy in bursts of X-rays and gamma rays. A magnetar flare in 2004 temporarily blinded every X-ray satellite in orbit, despite originating 50,000 light-years away, or roughly 294 quadrillion miles, approximately 473 quadrillion kilometers. The universe probably contains hundreds of millions of neutron stars, perhaps a few billion. Most are invisible, their emission too faint to detect, but those we can observe reveal exotic physics impossible to study on Earth: matter at nuclear densities, magnetic fields strong enough to distort atomic structure, space-time curved by immense gravity. Neutron stars are natural laboratories for extreme physics. With 200 billion trillion stars in total, perhaps 1/10 of 1% have died as massive enough stars to leave neutron stars. That's still hundreds of billions of neutron stars across the observable universe, each one a monument to stellar death, each one displaying physics at the edge of what matter can withstand before collapsing into a black hole. These objects remind us that the stellar census includes not just living stars but stellar remnants. White dwarfs by the tens of billions of trillions, neutron stars by the hundreds of billions, black holes by the billions. When we count stars, we're counting a population that spans the full life cycle, from formation through active fusion to eventual death and remnant stages. The complexity of this population, the diversity of stellar types and evolutionary stages, the range from the smallest red dwarf to the largest hypergiant, from newborn protostar to ancient white dwarf, from isolated single star to tight binary to massive cluster, all of it contributes to the richness of the census. 200 billion trillion stars isn't just a number. It's a population with structure, diversity, history, and ongoing evolution. It's the product of 13.8 billion years of cosmic chemistry and physics. It's the culmination of countless gas cloud collapses, fusion reactions, supernova explosions, and merger events. And remarkably, from one small planet, we've figured this out. We've measured it. We've understood it. We've placed ourselves within this vast stellar population and grasped our connection to it. Let's take a moment to appreciate the sheer improbability of what we've accomplished as a species. We evolved on a planet where the farthest our ancestors could see was perhaps 20 or 30 miles, or 30 to 50 kilometers to the horizon. For hundreds of thousands of years, that was the extent of our observable world. Then, in the last few centuries, an eye blink in evolutionary time, we developed tools that extended our senses far beyond biological limits. Telescopes that could see across billions of light years. Detectors sensitive enough to capture individual photons that have been traveling since the universe was young. Mathematical frameworks sophisticated enough to model cosmic evolution across 13.8 billion years. We didn't just count nearby stars. We counted galaxies across the observable universe, estimated their stellar populations, and arrived at a number: 200 billion trillion stars. This number comes from observations, calculations, and theoretical models built by thousands of astronomers over decades of careful work. Consider what goes into this estimate. Astronomers had to first understand that stars are distant suns, not points of light attached to a celestial sphere. They had to invent telescopes capable of resolving distant objects. They had to develop photography and later digital cameras to capture faint light. They had to build spectrographs to analyze starlight and determine chemical compositions, temperatures, and velocities. They had to discover the relationships between stellar properties like mass, luminosity, and temperature. They had to work out stellar evolution theory to understand how stars change over time. They had to realize that the fuzzy nebulae were actually distant galaxies containing billions of stars. They had to develop distance measurement techniques spanning from parallax for nearby stars to redshift for the most distant galaxies. They had to understand cosmic expansion, the Big Bang, and the evolution of structure in the universe. They had to account for dark matter and dark energy. They had to build satellites and space telescopes to observe in wavelengths blocked by Earth's atmosphere. They had to develop sophisticated image processing and statistical techniques to count galaxies in deep fields and extrapolate to the entire sky. Each step required overcoming technical challenges, developing new technologies, and refining theories. The process involved countless wrong turns, failed experiments, and revised estimates. But gradually, piece by piece, the picture came together. The number we quote today, 200 billion trillion stars, represents the culmination of centuries of work. It's not a wild guess, it's a measurement-based estimate with quantified uncertainties that continues to be refined as better data becomes available. This achievement speaks to human curiosity and ingenuity. We're not content to simply experience the world directly. We build tools to see farther, measure more precisely, understand more deeply. We ask questions like, how many stars exist? And then spend centuries developing the methods and instruments needed to answer them. The search for answers continues. The James Webb Space Telescope is revealing details invisible to previous instruments. Future observatories, like the Extremely Large Telescope and Nancy Grace Roman Space Telescope, will push boundaries further. Each new instrument will refine our census, finding faint galaxies we've missed, detecting distant objects invisible before, and improving our understanding of cosmic history. But we're likely close to the true number. The order of magnitude is solid. Whether the final count ends up being 100 billion trillion or 300 billion trillion doesn't fundamentally change the picture. The universe contains stars in quantities vastly exceeding human scale, numbering in the hundreds of billions of trillions. What does this mean for the future? For space exploration, for the search for life, for humanity's long-term prospects? The vast number of stars suggests numerous potential destinations, but also highlights the extraordinary difficulty of reaching them. Even the nearest stars are light years away. Distances so vast that with current technology, journeys would take tens of thousands of years. Future technologies might enable faster travel. Nuclear pulse propulsion could potentially reach a few % of light speed. Laser-pushed light sails might achieve 20% of light speed. But even at these speeds, reaching nearby stars requires decades of travel time. Reaching a significant fraction of the galaxy's stars would require thousands or millions of years. Exploring a meaningful fraction of the universe's stellar population is simply impossible given the expansion of space and the cosmic speed limit imposed by light speed. We're likely confined to our local region of the galaxy for any foreseeable future. Perhaps humanity will eventually spread to nearby star systems, establishing colonies on planets orbiting other suns. But the vast majority of those 200 billion trillion stars will remain forever beyond our reach. This constraint shapes the search for life. If intelligent civilizations are scattered across the galaxy, each one is probably isolated by distances measured in tens or hundreds of light years. Communication would take decades or centuries for a single exchange. Physical contact would be nearly impossible. The universe might be filled with life, perhaps even intelligent technological civilizations, but the distances ensure we remain isolated from each other. We'd be islands of consciousness separated by vast oceans of space, able perhaps to exchange messages across the void, but never to meet face to face. This isolation makes Earth precious. It's not just our home. It might be the only inhabited world we'll ever physically access. If life exists elsewhere, and the numbers suggest it probably does, we're unlikely to find it nearby. The volume of space we can realistically explore in the foreseeable future is tiny compared to the galaxy, let alone the observable universe. This reinforces the importance of preserving Earth's biosphere. We're custodians of something potentially rare and definitely precious. Life on Earth represents at least one instance of matter becoming conscious, of the universe developing the ability to understand itself. That's remarkable and worth protecting. The cosmic perspective also affects how we think about long-term human futures. On cosmic timescales, human civilization is barely beginning. We've existed for perhaps 10,000 years in any organized form. The universe will continue for trillions of years. Even individual stars like the Sun will shine for billions more years. If humanity survives, if we navigate the challenges of the next few centuries and establish ourselves as a multi-planet or multi-star species, we could potentially exist for millions or billions of years. On those timescales, recorded history becomes a brief prologue. The real human story would be whatever we accomplish over the vast stretches of time ahead. But we're not guaranteed to survive. Civilizations can fail. Species go extinct. Perhaps most technological civilizations don't last long, which might explain the Fermi Paradox. Perhaps we're witnessing something rare, a civilization at the critical juncture where it either establishes itself for the long term or fails and dies out. The stakes are high because the potential is immense. If we succeed, humanity could witness the evolution of stars, the changes in galaxies, the long, slow future of the cosmos. We could become truly long-lived, persisting for timescales comparable to stellar lifetimes. We could explore our region of the galaxy, establishing presence around thousands of stars. We'll never visit most of those 200 billion trillion stars, but we might visit thousands or tens of thousands in our cosmic neighborhood. We might establish civilizations around multiple suns. We might become a truly spacefaring species, at home among the stars rather than confined to one small world. Or we might fail. We might destroy ourselves through war, environmental collapse, or other catastrophes. We might be a brief flicker, one more species that briefly attained consciousness and technology before vanishing. The universe wouldn't notice. Stars would continue shining. Galaxies would continue evolving. The cosmos would proceed indifferent to our absence. This uncertainty makes the present moment critical. We're at a turning point. The decisions we make in the coming decades and centuries will determine whether humanity has a long future among the stars, or whether we're a brief anomaly, a temporary spark of consciousness that appeared briefly and then went out. Understanding that we're one planet among countless possible worlds, orbiting one star among 200 billion trillion, provides perspective. We're not the center of the universe. We're not cosmically significant, but we're here. We're conscious, and we have the opportunity to persist and potentially spread among the stars. That opportunity is worth preserving. The fact that the universe contains such vast numbers of stars, such enormous potential for worlds and life, makes our existence both less special and more precious. Less special because we're likely one among many. More precious because consciousness and understanding are probably rare enough that each instance matters. As we close this exploration, let's reflect on what we've learned. We started with a question about counting, about comprehending large numbers. We built an understanding of millions, billions, and trillions. We examined how astronomers count stars and galaxies. We explored stellar types, evolution, and death. We looked at galaxy diversity and cosmic structure. We discovered that the observable universe contains approximately 200 billion trillion stars based on observations of about 2 trillion galaxies, averaging roughly 100 billion stars each. This number is our best current estimate, refined through decades of increasingly sophisticated observations and likely accurate to within a factor of 2 or 3. We learned these stars aren't static. They're born in molecular clouds, live for millions or billions or trillions of years depending on mass, and die as white dwarfs, neutron stars, or black holes. They exist in diverse systems, from isolated singles to tight binaries to massive clusters. They span a range from tiny red dwarfs to enormous hypergiants. We found that most stars probably have planets, suggesting hundreds of billions of trillions of worlds scattered across the cosmos. Some fraction of these worlds orbit in habitable zones where life might potentially arise. The absolute numbers could be staggering, even if the percentages are small. We understood that stars are element factories, creating through nuclear fusion the heavy atoms that make planets and life possible. Every atom in our bodies, except hydrogen, was forged in stellar cores and scattered by stellar deaths, connecting us intimately to the cosmic story of stellar evolution. We saw how galaxies interact and merge, reshaping their stellar populations over billions of years. We learned about exotic objects like quasars, neutron stars, and black holes that push physics to extreme limits. We glimpsed the cosmic web of structure stretching across the observable universe, and we appreciated the remarkable achievement of measuring all this from one small planet. The fact that conscious beings arose and figured out how to count stars across cosmic distances speaks to human capability and curiosity. When you walk outside tonight and look up at the sky, remember what you now know. Those visible stars are the nearest few thousand of 200 billion trillion. Each point of light represents a massive nuclear furnace, most likely with planets, potentially with life, existing in a galaxy somewhere across the cosmic expanse. The light entering your eyes has traveled for years or centuries or millennia to reach you. You're connected across space and time to those distant suns. You're made of atoms they created. You're part of the same cosmic story that includes all 200 billion trillion stars. This knowledge should inspire wonder. The universe is vast, beyond human scale. It contains more stars than grains of sand on our beaches, more stars than we could ever hope to visit, more stars than we can meaningfully imagine. Yet we've counted them. We've measured their distances. We've understood their natures. We're small and brief in cosmic terms, but we're also extraordinary. We're conscious matter that can contemplate the cosmos. We're the universe's way of knowing itself. That's remarkable and beautiful and worth celebrating. Thank you for joining me on this journey through the cosmos. If this exploration has deepened your sense of wonder, please like and subscribe. It helps create more content exploring the profound questions about our universe. And may you never look at the night sky the same way again. When you see those stars, remember, 200 billion trillion of them. Each one a sun, each one possibly the center of its own system of worlds. Each one part of the grand cosmic story of matter and energy evolving across billions of years. We measured them, we counted them, we understood our place among them. That's what makes us human. That's what makes this moment in cosmic history special. We're here, we're conscious, and we've grasped the magnificent scale of the cosmos we inhabit. The cosmos awaits. 200 billion trillion stars shine across the observable universe, each one a testament to the grand processes of stellar birth, life, and death that have operated for nearly 14 billion years. We've spent this time together exploring not just a number, but what that number means, where it comes from, and how it connects to our own existence. That's the real answer to the question of how many stars exist. Not just the count, but the understanding that comes with it. What we do know is that we're part of this cosmos. We're made of elements created in stars. We live on a planet orbiting a star. We're capable of understanding our place among 200 billion trillion stellar neighbors. That understanding is part of what makes us human. We can look up at the night sky and know what we're seeing. We can calculate distances to galaxies we can never visit. We can count stars we can never see individually. We can grasp, at least intellectually, the scale of the universe that contains us. This knowledge should fill us with wonder. The fact that conscious beings arose on a small planet and figured out how many stars exist in the cosmos is remarkable. We should never lose that sense of awe at what we've discovered and what remains to be discovered. So the next time someone asks how many stars there are, you have an answer. Approximately 200 billion trillion in the observable universe, with the possibility of far more beyond our cosmic horizon. More stars than we can ever count individually. More stars than we can meaningfully visualize. More stars than we can visit, even in principle, given the vast distances involved. But each one real. Each one a massive sphere of plasma, fusing elements, lighting up the darkness. Each one part of the grand structure of galaxies and clusters and filaments that make up the large-scale architecture of the cosmos. We're here for such a brief moment in cosmic history. The universe existed for billions of years before we arrived, and will continue for trillions of years after we're gone. But right now, in this moment, we exist. We can think about these questions. We can marvel at the answers. That's the real meaning of the number. Not just 200 billion trillion stars, but what that number represents. The vastness of the cosmos, the incredible diversity of stellar types and life stages, the chemical enrichment that makes complex chemistry possible, the possibility of countless worlds and perhaps countless other forms of life scattered across unfathomable distances. We're small, we're brief, but we're here, we're conscious, and we can understand our place among the stars. That's extraordinary. Thank you for joining me on this exploration. If you've found value in this journey through the cosmos, please like and subscribe. It helps me continue making content that explores the deep questions about our universe. And remember, when you look up at the stars tonight, you're seeing just the nearest few thousand of 200 billion trillion. The universe is vast beyond measure, filled with more stars than grains of sand on all our beaches, each one a sun, each one potentially the center of its own system of worlds. Good night, and may you carry with you a sense of wonder at the magnificent scale of the cosmos we're privileged to inhabit.